Welcome back. Today we're going to take a look at accuracy and precision. That's how we're going to start our video 2 for the experimental unit notes. Now you probably remember this from chemistry. Accuracy is going to be how close a measurement is to an accepted or a predicted value. So in chemistry you probably were given the accepted values. In physics, sometimes we like to go ahead and make a prediction based off of a formula, and we use that prediction as our accepted value. Now for precision, basically, how sure are you of your measurements? When you go to find precision, you need multiple measurements. This means doing multiple trials where everything is the same. Now, you probably have seen this graph here. This is found in every textbook, it seems like, the Bullseye Model here. And, if something is accurate and precise, that means all the measurements are grouped closely together in the bullseye. If something is precise but not accurate, everything's grouped together, but it's not on the bullseye. If you have something that is imprecise, but you got some measurements that are accurate, and then this last one, all chaos breaks loose. Nothing's accurate and nothing is precise. Now let's take a look at an example. Suppose you want to find the mass of a gold ring. And let's say the purpose is you want to sell it. Well, you need to have an accurate mass so that you can get a fair market value for the ring. Now, if you were to hold the ring in your hand and guess the mass to be somewhere between 10 and 20 grams, well, is this measurement accurate and or precise? Well, it's definitely not accurate because you're not using any tools. It's not precise because you're only taking one measurement. So if we wanted to get both an accurate and precise measurement of the mass, well, we would need to use some standardized tool, such as a triple beam balance or an electronic scale. We would have to make sure we calibrate it. And then we would want to take its mass multiple times to see if the scale is precise. In fact, I would probably take a few measurements on an electronic scale, take a few measurements on a triple beam balance, take a few measurements on a separate scale altogether, and then figure out the precision of all those measurements, and that would help me figure out if it's accurate. Also, something else to get the accuracy, I might look up the density of gold, find out the volume of the ring, probably by submersing it in some water and seeing how far up the water travels, and then I could do a quick calculation of the mass. So to see what the mass should be, then compare that to the mass that I measured, just to find out if it's accurate. So how could we measure some accuracy and precision? I'm going to start with the precision first. We represent it by calculating something called the standard deviation. And sometimes you'll see me call this the average deviation. So, for example, I'm using 3 different scales to find the mass of a child. And the readings of the scales are 65, and then I have my uncertainty of 0.5, 66 with an uncertainty of 0.09, and 67 with an uncertainty of 0.1 kilograms. And I want to find out how precise these scales are. Well, first off, When you go to find precision, don't worry about the uncertainty aspect of it. Okay, we're just going to look at the best estimates. So what you want to do first is write out the numbers, and then you want to calculate the mean. And looking at this, the mean is obviously going to be 66. You then want to subtract the mean from each measurement and take the absolute value so that they're always positive. So here I get 1, 0, and 1. Now it's called average deviation for a reason. You want to calculate the mean of these three numbers. So for here I'm getting 0.6 repeating is the mean of these individual deviations. So I would say then that the mass of this child would be 66 plus or minus 0.6 repeating kilograms. That would be the mass of the child. And here you can see that this time the average or the standard deviation becomes our uncertainty of the measurement. And that's why I wanted you to cross out off the uncertainties earlier, because we're now going to use the precision for our uncertainty. For accuracy, we represent it with something called the percentage error. So, for example, the acceleration due to gravity is 9.8 meters per second squared. However, a student in an experiment measures it to be 9.6 meters per second squared. So, to find out the percent error, what I would do is I would take the 9.8 minus 9.6, absolute value of it, divided by 9.8. So basically you're looking at the difference in the measurements, or how far off the measurement is from the accepted, divided by the accepted. And then I would multiply that by 100 to turn it into percent. And we would see that here we have a percent error of 2.0%. Typically anything less than 10% is good. All right, let's take a look at another example. In this example, an experimenter is measuring the time it takes for a ball to fall 1 meter. The experiment is conducted 5 times with these measurements. So basically, this experimenter does 5 trials, and that's what you want to do. You want to do multiple trials where everything is the same. So this person is taking the ball, measuring it to be as close to 1 meter as he or she can get it, and then dropping it and timing it. And they're doing it 5 times. And these are the 5 measurements here that you can read. So, using these measurements then, what would the reported time be? So, since I want to report the time, I'm going to find out precision. So, once again, I'm going to just, it's always a good habit to write down your uncertainty, but I'm not going to worry about it for this part. So, I'm going to cross off the uncertainties, and I'm going to go ahead and write out these times. I got 4.5, 4.4, 4.6, 4.5, and 4.4. And what we want to do is we want to find the mean. And the mean is 4.5. I then take that and I subtract it from each individual measurement, taking absolute values because I only want the positiveness. And here I get 0, 0.1, 0.1, 0, and 0.1. These are our individual deviations. So I have 5 deviations. So I will now find the average of those individual deviations. So I get 0.06. So the time it takes for this ball to fall is going to be 4.5 plus or minus 0.06 seconds. That's how long it takes the ball to fall 1 meter. Okay, now, when you're doing calculations for an experiment, uh, what's kind of cool is that one of the things that we found in physics is that much of what we see in nature can be modeled with mathematical formulas. So an understanding of math is very important. So some skills that you will need. I mentioned this before, but you need to know how to convert units. There is no getting around it. You have to be able to convert units. And if you have any problems with that at all, make sure you see me so that I can help you convert units. You need to be able to solve for unknowns in algebra. And I promise you the most I will give you would be 2 unknowns. So you would have to have 2 equations to solve for those 2 unknowns. And then finally, you need to know how to do statistical calculations. Now, there are a ton of statistical calculations in experiments and experimental physics. This year, we're just going to focus on finding percent error and standard deviations. If you were to pursue physics at a higher level, you could then learn more advanced statistics there. And there's a lot, and I would encourage everyone to study statistics. Um, Statistics is more applicable to what we need in society than calculus, I believe. So learning stats is very, very important for more than just science. All right, that concludes this video.